So in our first section, we just want to learn some terminology. So our first question is, what exactly is a differential equation? The simple answer to that is it's an equation with one or more derivatives in it. So we'll start with an ordinary differential equation, which is basically just an ordinary derivative with respect to just a single independent variable. Let's look at some examples. So in our first example, we have a first derivative with respect to x. In our second example, we have a second derivative, and it's implied that it's in terms of x. So they are both in terms of x. So the order of a differential equation is the highest derivative appearing in the equation. Okay, so for our first example, we have dy dx equals minus 4x squared. So clearly we only have the first derivative. So the highest derivative in this equation is a first derivative. So we call this the first order. Our second example, we have the highest order is the second derivative. Y double prime is the second derivative. So this is a second order. In this example, we have y to the fourth in parentheses, and so this is a fourth order. So just to remind you for notation, here's my note, is that the highest that we can do either one, if we have 3 ticks, that's the third derivative, we can also write it as y to the third power. But you have to put it in parentheses, otherwise it's a power. It's not a power, it's a derivative. That's the third derivative. So, a general nth order ordinary differential equation can be written as a function in terms of x, y, y prime, all the way up to the nth derivative, which is equal to 0. So here's our notation for the nth derivative. And the normal form of a differential equation, we basically are just taking the nth derivative and setting it on one side and having everything, all the other variables and derivatives to the other side. Wait. The first order ODE in normal form would be our highest derivative, which would be our first derivative, dy dx, and it's equal to all the lower derivatives, but there are none, and variables. So there we have it. That's the normal form of a first order differential equation. Let's write out the second order. Can you guys do it? Yeah, so therefore we have our second derivative on the left, and it's going to be written in terms of these variables, x, y, and our first derivative, y prime. Good, very good. And there we have it. Okay, so linearity. So basically, it's just an nth order differential equation, ODE actually. It's linear if f is linear in these variables and derivatives, meaning they're not, there's no power to them, or they're not in the denominator or anything, but it's not necessarily linear in x. So here's what a linear ODE looks like. So basically we have our derivatives in y, and there's no power to them, they're not in the denominator, but we also have our functions in front, that are in terms of x, and this is just, this is in terms of x. It could be x squared, it could be cosine of x. So all of these coefficients, per se, in front of my nth derivative, n minus 1 derivative, all of these are my coefficients. Those don't have to be linear. Okay, so the only ones that have to be linear are those. So that's what a linear equation looks like. Let's look at an example. So here's an example, and I went a little crazy here, threw in some powers and exponentials and rationals as coefficients, just so you can see when it's the x variable, it doesn't have to be linear. Okay, so again, this is a second order, this is the highest derivative, so this is a second order linear ODE, ordinary differential equation. Okay, that's what it looks like. Okay, and this is our g of x right here. Sometimes we want 0 on that side, and sometimes it's okay to throw the g of x over there. So we're not very picky about that right now. Let's look at some more examples. So this example at first glance appears to be linear, but the problem is we don't have we have to isolate our second derivative to put it in normal form. And now we can see y is not linear. So this is not linear. Or we can call it non-linear. So let's look at this example. We have a second derivative, and we don't really need to isolate that to tell if it's linear or not, because this is cosine of y. It's not y by itself. There's no coefficient of y there. Cos is not a coefficient. So this is non-linear. We would, if we had cosine of x, y, that would be our coefficient. That would be good, but that's not what we have. That's not the same. So this example, again, we have a y squared is not linear. So this, again, is, we're going to call that non-linear, a non-linear DE. So our last example, just because we've had the last couple examples that were non-linear, we have our y, our second derivative, and our y, and we do have a coefficient that's x squared. We're allowed to have x not be linear, so this is definitely a linear DE. It's actually a second order again. Okay, so these are some questions I actually like to ask on our first exam, and sometimes even on our final. The quick little questions that I can ask on there. So a solution to a differential equation, we can call it y. It's a function which basically it solves it. And what that means is just when you plug it into the DE, it's a true statement. Here's our example. We're going to show that this DE has a family of solutions. That's our equation, our solution y equals x squared over 4 plus c quantity squared. And we're also going to show that that DE has a singular solution, which is basically just not part of the family. It's a constant in this case. So part A, our DE and we want to show that that equation is our solution by plugging it in. So we can definitely plug in for y. So over on the right side, it's x, y is x squared over 4 plus c quantity squared, but this is y to the half, so we need to the half. See that? This is y, and they're both to the half power. On the left side, we need to plug in for dy dx. Well, we have y is equal to x squared over 4 plus c quantity squared. So in order to plug in dy dx, we just take the equation, we just take the derivative of our solution to find dy dx. Dy dx. We'll power rule, I should say, and now chain rule times the derivative of the inside. And clean it up. And plug it in. And now simplify this on the right. So over on the left, we can just keep it that way. Maybe put the x first. And on the right, the x is there. We have power to power, which they cancel out because you multiply. 2 times 1/2. So it appears that both sides are identical, and that was our goal. In order to be a solution, you plug it in, you get a true statement. That is true, therefore y is a solution. Therefore, y equals, what is it? This one right here. X squared over 4 plus c squared is a solution. And we see it works for many, many different c's, and that's why we call it a family of solutions. B, so y of x equals 0. We want to be able to plug in for y, so we basically have y equals 0, and we need to plug in for dy dx, so y prime or dy dx equals 0 also, derivative of 0, 0. So we get, for this equation, let me write the equation, dy dx. So this is 0, you plug in 0, and then we have 0 to the half power, because y is 0, right? So we get 0 equals 0, and that's true. We also call that our trivial solution. Our trivial solution is y equals 0. So just something we'll be looking at later in another section, and we'll be looking at graphs of solutions. So the solutions being y. So the graph of an ODE is called either a solution curve or an integral curve. So here we have the general solution or the family of solutions, which was our example, our previous example. So there's 2 names to it. And to be honest, I think general solution is the one we use more in this book. And it's basically just a solution that contains an arbitrary constant. Basically, it had a c in it. So it's basically a solution from which all solutions can be obtained. It's also, another name for it is called an n-parameter family of solutions. So another little fact that's helpful in this class is usually the number of arbitrary constants equals the order of the ODE. So for example, we'll be solving first order differential equations at the beginning, and first order is just one derivative, so we'll have one constant. The example we saw above was a first order. When we start solving second order, there'll be 2 constants, C1 and C2, in our general solution. And just another note about ODE. Most of this course is ODE, ordinary differential equations, and that's why I drop the O quite frequently. The very last chapter, chapter 12, we will be covering partial differential equations. So just wanted to get that fact down because it's pretty important. First order DE will just have one constant. Last fact of the day, a particular solution will be free of arbitrary parameters. Basically, they don't have any constants in it because it's a particular solution, not family of solutions. Okay, that concludes our first section